Hello, friends.
Yes,
First,
sir.
I am Dr. Kishore Mangal. First of all, I would like to thank Dr. Tapesh Bansal sir and Young India Intensivist Forum for providing me this opportunity and for giving a platform to discuss such an important topic, which we actually do it on a daily basis. But the approach, that the Steward's approach, because it is bit complex, we don't use it bedside. But at the end of this lecture, we will be knowing that using it is this approach is probably not that difficult, and it can be helpful in many situations. So first of all, I would like to outline my presentation, and I'll be covering introduction to this Stewart's principle. What are the core concepts and explanation of these principles? How do we practically apply this principle? Clinical status and its clinical Stewart's explanation, case examples, and finally the summary. So, who was Peter Stewart? So, he was a Canadian biophysicist who used to taught in the university, and he used to taught mathematics, physics, chemistry, and biology. And the fundamentals he taught was that science is unified. Okay, science is one, and the all the four branches which I have said are branches of the science. Okay, so you cannot keep it separately. Okay, and he tried to combine all these four streams and centered on the application of mathematical and analytical methods to the regulation of physiological systems. So he combined these things, and ultimately when he saw this acid based physiology, he wrote a book on this, and that is a landmark in understanding the acid based physiology till today. What was Stewart's observation on traditional methods of ABG analysis? The conventional understanding of acid-base balance is cluttered with jargon, chemically meaningless derived quantities, a misunderstanding of what is happening, and an artificial use of the Henderson-Hasselbalch equation as the single equation determining acid-base balance in any body fluid. Quite strong words and disagreement to the principles which were being followed at that time and also in today's times as well. So definitely we need to go deep into it. So what he continues to say is the Henderson-Hasselbalch equation is just one of the 6 equations which must always be simultaneously satisfied. So by using his mathematical skills and the principles of physiology, biochemistry, and others, he was able to deduct 6 equations, and HH equation was just one of them. And he concludes that all disturbances of acid-base balance must result from changes in the independent variables and only the independent variables. Okay, so independent variables we will be discussing in next few slides. But this line is very important. What he focuses is on independent variables, and from there he will be able to analyze the acid-base balance. So if we simply study acid-base balance, it is the role of the buffers to maintain our pH. The most common buffer is carbon dioxide bicarbonate buffer. Okay, we know this equation H2O plus CO2 with carbonic anhydrase converts into H2CO3, then H plus bicarbonate. This happens in RBC and plasma. So if the patient is developing respiratory acidosis, pH will be decreased. There will be respiratory stimulation, respiratory rate and depth will increase, CO2 will go off. If there is metabolic acidosis, traditional teaching is that renal compensation will start pH because pH has decreased, and kidney will try to increase the rate of H plus secretion, and that is how the balance is achieved. And based on these, we have our traditional approaches, Henderson-Hasselbalch and Sigard-Anderson's base excess approach, and both the approaches are basically based on this CO2 bicarbonate and H plus ions with fixed acids and buffer base. But we know that this is not the only buffer. The chemical buffer system also includes phosphates and proteins. So it is usual and it is understandable that why should we focus only on one system of bicarbonate? Okay, so we need to incorporate phosphate and protein buffer systems into the analysis of ABG. Although whenever compensation has to happen, bicarbonate is the quickest one, but that doesn't mean that the protein and phosphate do not change at all. Other than that, the second line of defense is physiological buffers, which includes respiratory mechanisms and the renal mechanisms. Respiratory mechanism, all the approaches agree on the basis of CO2 excretion that happens, or the CO2 control that happens. But for the renal mechanism, traditional approaches says that it increases, the kidney increases your H plus excretion. Right. So this is our traditional approach. So H plus ion increase, excretion is increases, and which results into absorption of the bicarbonate. But what actually happens, we know that we have proximal tubule, we have collecting tubule, we have lot many transporters, and sodium is potassium transporter is there, bicarbonate sodium is there. Then we see here ammonium is getting transported into the tubule, chloride is getting exchanged, and ultimately H plus ion, which has to be removed from tubular lumen, combines with ammonium, and then it is combined with filtered chloride, and it is excreted in the form of ammonium chloride. So traditional approach of H plus ion excreted to maintain balance is wrong. This explanation is wrong. And the Steward's approach here, now we will understand what happens here is that the acid handling by the kidney is mostly mediated through ammonium chloride, and between that ammonium chloride, changes in the chloride balance are the most important. Why? Because ammonium is a weak anion and chloride is a strong anion, and since chloride is excreted, that allows body to retain strong ions, which are sodium and potassium, and this strong ion was cation increase and anion decrease results in change in the strong ion difference, which causes the change in the plasma pH. So here the baseline is that the excretion of chloride without strong ions results in the changes in the pH and improvement of the acidosis by the kidney. So the Steward's approach provides the explanation and insights into the physiology and the pathophysiology which is occurring. That is why it seems to be superior to the traditional approaches. So coming to the core concepts of Steward's approach, basic principles determining the equation of H plus ion in any body fluid are very simple. First is electroneutrality must be conserved. And it is true for any fluid, whether it is water, plasma, or blood, or ECF, ICF, any fluid. The electroneutrality will be conserved. That means positive ions and negative ions will be equal in number. The second principle is mass must be conserved. That means suppose you have a phosphorus. Okay. Now the phosphorus is converted between H2PO4 minus to HPO43 and H3PO4. So it is always getting converted between different things. Okay, different charges. But the total amount of phosphorus will remain same. That is what is mass must be conserved. And all dissociation equilibriums must be met, especially for weak anions. So, understanding these three principles, and since multiple mechanisms will influence concentration of the H plus ion, like CO2, the bicarbonates, the albumin, the phosphorus, the sodium, strong ions. So, because so many things can affect the concentration of H plus, solving them all results in a set of simultaneous equations. And if we know the equations, and if we know the equilibrium value, if we know the dissociation constants, then we can derive a formula. Although by seeing so many equations, the overall analysis will be very complex mathematically. A lot of calculations will be required. But if we have the computers, we can solve it incomplete. The six equations which were given are these, and it depends on dissociation equilibrium of water, bicarbonate, carbonate ion, and conservation of mass of A and electrical neutrality. But do we need to remember all these things? Probably no. And is it required? Probably no, for our clinical practice. And if we see into the further equation solution, so it is very, very difficult. We see here that there is some fourth order polynomial quadratic equation is there, which is very, very difficult or practically impossible for most of us. We cannot solve it, especially by using hands. We need computer support. So should we stop Steward's application? Should we stop this analysis? No. Why? Because what we can do here is either, of course, we can use computer. We have one website which is acidbase.org, where we can, if we have all the data from the ABG, we can put that data into the ABG and it will give you the answer. Or we can use our brains and can simplify the complex equations into simple equations, which can be used at bedsides. And this is what we are going to learn in next few slides. Coming to the core concept 2. So, as we had discussed earlier as well, the H plus ion concentration is determined by two variables. One is independent variable and second is dependent variable. Now, amongst this independent variable is the primary cause, which is going to affect H plus ion, and it also determines the dependent variable, which is the secondary effect. So, ultimately, it is the independent variable which is the most important thing which we have to focus upon. So what is the definition of independent variables? So independent variables are values which are or the measurements which are determined by processes or conditions which are external to the system or the fluid. That is, the changes happening in the independent variables are imposed on the system rather than being determined by it. So local pathology or local changes in the fluid will not be able to change this independent variable. And dependent variables are variables which are determined internally by the system. These are determined by the equations, that is the chemical equation which determine the system, and can be altered only by changes in the value of the independent variables. Right. So independent variables are not locally affected, but affected by systemic problems, and the dependent variables are locally affected. So what are the three most important independent variables as per Stewart? One is the CO2, that is the carbon dioxide level in the arterial system. Second is the strong ion difference, which also is known as SID. This SID is the electrolyte composition of the blood, and this is controlled by the kidney. And CO2, as we all know, is controlled by the respiratory system. And third is the weak acid, or we also called it as ATOT. So ATOT is weak acid, that is predominantly a protein concentration, and it is mainly controlled by liver and the metabolic state. So the acid-base physiology incorporates respiratory, kidney, and liver and the metabolic system. Okay, so this is far more comprehensive. And every change of these variables, PCO2, SID, and ATOT, will change the pH. What are the dependent variables? So H plus ion, OH minus ion, CO3, anion, AH, HCO3. These are all dependent variables, especially the H plus ion and the bicarbonate ions. If we remember the traditional approaches, we start with pH, we calculate, and from the HH equation, the level of the HCO3, and we derive everything from there on. But as per the Stewart's principle, these two things are dependent on the independent variables. Okay, so if there has been a change in the H plus ion or in the OH ions or the HCO3 level, definitely some independent variables must have changed. That has led to the change in the H plus ion and the HCO3 ion. So these are effect of the independent variables. So here in further analysis, we will less see these things and more on focus will be on the independent variables. Now, further going into the detail, third concept is the concept of strong ions and the weak ions. So based on the dissociation property of any compound, aqueous solution contains strong and weak ions. Strong means strongly dissociated. Okay, does not mean more concentration or strong solution, but it is related to the dissociation. So strong ions in solutions are always fully dissociated and thus they exist only in the charged form. For example, sodium. Sodium is always and always present as Na plus in the water. Chloride. Chloride is always present as Cl minus. It is not present as HCl, or sodium is present as NaOH. Okay, so it is never like that. So these are strong ions. Now coming to the weak ions are only partly dissociated when dissolved in water. So they are always in equilibrium between themselves. So the solution containing the weak acid and plus the products of its dissociation. So it will be H plus ion plus A minus is equal to Ka into Ha, where Ka is the dissociation constant. This is only to understand what is happening. If we are not able to remember these equilibrium equations, it is not going to affect your calculations later on. But we need to understand what is a strong ion and what is a weak ion. So strong ions are fully dissociated, weak ions are partly dissociated. So if we divide all the ionic species present in plasma, strong ions are sodium, potassium, calcium, magnesium, chloride, lactate, sulfate, NEFA, which is non-esterified fatty acids, keto acids, proteins, and phosphates with fixed negative charge. Okay, so this amount, protein and phosphate with fixed negative charge, is very, very small, and we can, in practically, we can avoid or we can remove it. Then we have weak ions, which includes non-volatile and volatile. Volatile is where it can be changed with the change in the respiration, that is the CO2. Okay, so CO2, carbonic acid, and bicarbonate is volatile weak acid, and non-volatile weak acid predominantly contains protein phosphates and then uric acid also. Okay, so if we see here, we have three different ions: strong ions, non-volatile weak acids, and volatile weak acids. So strong ions, it is having cations as well as anions. Mainly anions are chloride and lactate. And the difference between the strong cations, that is sodium, potassium, calcium, magnesium, and strong anions, chloride and lactate, which are the predominant one, is called as SID, which is the strong ion difference. Total amount of non-volatile weak acid, which is predominantly protein and phosphate, forms the A dot. And volatile weak acid, that is the CO2, is our third independent variable. So depending on strong ion and weak ions, we calculate the the Steward's approach is based upon on these things. So the first independent variable, PCO2, we know that carbon dioxide is produced by all the cells and it is easily traverses through the cell membranes, ISF, blood. So the diffusion is very, very fast. It is excreted from the body by the lungs. The level of PCO2 is under sensitive and powerful feedback control via the peripheral and central chemoreceptors. Whenever there is change in the CO2 level, chemoreceptors are activated and it gives you the brain the signal to respire. Okay, and we can change our CO2 levels from there. So what do we understand here is that the CO2 level is not controlled at the level of fluid inside the cell or in the blood or in the ISF, where it is actually being controlled by the chemoreceptors. Right. So PCO2 in arterial blood and all body fluids is effectively set by mechanisms other than the chemical equilibria occurring in that particular fluid. Right. So here an external factor, which is the chemoreceptor, is controlling the system. Therefore, it is an independent variable, right? So PCO2 is controlled by brain via central and peripheral chemoreceptors, and the local chemical equilibria of the fluid is not responsible for control. That is why it is an independent variable. This is the first variable. Coming to the second variable, which is SID, it is known as strong ion difference. We have already discussed that it is the sum of all the strong cation concentrations in the solution minus the sum of all the strong anion concentrations in the solution. So here these are the strong cations, strong anions, and the difference between two is the SID in the ideal condition. So these are all these strong cations and anions. And ultimately, SID represent the net charge which must be balanced by charges on the weak acid in the solution for the electrical neutrality. Okay, so if these are strong anions and this is the remaining one, so this is going to be the strong weak anions. Okay, so SID is equal to the all the negative charges of the weak anions or weak acids in the fluid. So why it is an independent variable? So again, for a variable to be independent, it has to be controlled from outside system rather than the local fluid. Okay. So if we go into all the things like sodium, potassium, calcium, magnesium, chloride, and lactate, none of these ions are produced or consumed in a particular fluid. And the concentrations are imposed on the solution from outside and also controlled by the outside mechanisms. Like sodium, the absorption is from GI tract and excretion is controlled by kidney. Similarly, for calcium, magnesium, the increase is because of the GI absorption and decrease and or the excretion is from the kidney. So kidney is the most important regulator for most of these ion concentrations. So if kidney is the most important regulator and it is outside the fluid, that is, it is not inside the cell or ISF or in the blood, so the changes in the SID is mainly regulated by the kidney, and it is to control the H plus ion level, as we had discussed previously as well. So kidney regulates SID, and that is why SID is also an independent variable, right? So for that to happen, if the control is outside, kidney is also outside, SID becomes an independent variable. So this is important. And coming to the third variable, which is the ATOT. So ATOT, what is ATOT? So abbreviation ATOT represents the total amount of non-volatile weak acid present in the system. So it is collectively known as HA, and it includes mainly phosphate and albumin, but also in small amount uric acids and other unmeasurable anions. The law of conservation of mass is applied here, and it means that the total amount of A, that is the weak anions, or the symbol becomes ATOT, in the system must be constant, and conservation of A can be represented as ATOT is equal to HA plus A. Okay, and HA can be converted into A depending on the availability of the H plus ions. So if H plus ion increases or decreases, it will change the value of HA to A minus or vice versa, but the total amount will remain the same. So A dot remains the same. Now, why it is a independent variable? Because again, it is not produced locally, but it is being produced by the liver and by the local metabolism. Okay, so like protein and phosphates, they are not regulated by the fluids. Okay, so that is why protein and phosphates become the major non-volatile weak acids. And amongst the two, albumin is a major contributor. So when we do it practically, ATOT can be replaced by the albumin alone, especially if the phosphorus levels are not very high, right? So practically, if we come to the gist of these three things, so we have three independent variables: strong ion difference, PCO2, and protein concentration. And these three things lead to changes in the water dissociation equilibrium which will change H plus ion concentration and OH minus concentration and will lead to change in the pH. So this is the basically difference between HH equation and Steward's approach. In HH equation or the traditional approach, we have PCO2 and base excess. PCO2 results in respiratory problem, base excess and bicarbonate results in metabolic problem. This is in pH, where here in Steward's approach, the metabolic is explained better. It is converted into two major things, which is SID and ATOT. And amongst all these things will lead to changes in SID and can lead to metabolic changes. And ATOT can also lead to changes in metabolic component, leading to changes in the pH. Now coming to application of Steward's principle. Okay, so we know that these are the three independent variables, and changes in the three will cause the variation of acid-base effect. So PCO2 changes are similar to what we see in the traditional approach, so that is not changed a bit. If the PCO2 is high, then it is respiratory acidosis. If PCO2 is on the lower side, this is respiratory alkalosis. We know that. What will happen if the SID increases or decreases? So if SID increases, that leads to metabolic alkalosis, and if SID decreases, that leads to metabolic acidosis. Whereas for the ATOT, it is reverse. So if ATOT is increased, it leads to metabolic acidosis, and if ATOT is decreased, that leads to metabolic alkalosis. So effect of major strong ions, this we have to remember like this table. Again, I am repeating in a different way. So we know that the SID is majorly formed between the sodium and the chloride. So if the sodium concentration is increased in the body, what will happen? And if chloride remains same, then the strong ion difference will increase, because strong ion difference is mainly sodium minus the chloride. And if sodium is increasing in the body, to balance that, we will have OH minus 2, which is there in the water as the increase to compensate for the electroneutrality. If plus is increasing, then we need to increase some minus. Okay, so OH minus will be increased and it will be metabolic alkalosis. Bicarbonates or the OH minus is increasing. Right. So if sodium is increasing, it will increase SID and it will increase the pH. So these all the three things are on the same direction. Sodium increase leads to SID increase, leads to pH increase. Similarly, if the sodium is decreasing, that means SID or the strong ion difference will also decrease and the pH will also decrease, because OH will be reduced and H plus will be increased. So there will be metabolic acidosis. What will happen if chloride is increased? So if chloride is increased, the SID decreases. Okay, because SID is again sodium minus chloride. So if sodium remains normal or same and the chloride is increasing, it reduces the strong ion difference. And when the strong ion difference reduces, it leads to metabolic acidosis. Or to understand simply, chloride, although is completely dissociated, but it is in the form of H plus and Cl. So if Cl is increasing, ultimately H plus will also increase. And if H plus is increasing, ultimately the body will have metabolic acidosis. And if the chloride is decreasing, it will lead to increase in the strong ion difference, and increase in the strong ion difference will lead to metabolic alkalosis. So hypochloremia, the patients are having metabolic alkalosis. So hypernatremia and hypochloremia causes metabolic alkalosis. Hyponatremia and hyperchloremia causes metabolic acidosis as per the principles of Stewart. Right? What are the effect of major weak proteins? So major weak proteins mainly are albumin and phosphorus. In critically ill patient, we often see that the albumin levels are on a lower side. The patient's albumin is 1.5, 2 or 2.5, so it is reduced. So what it does to the ATOT, so the ATOT is also going to reduce. So now again, as we had seen in the previous slide, the chloride level reduces, then the patient will also have reduction in the H plus ion, right? because the chloride is the dissociation from the HCl. So if chloride is low, H plus is low. Similarly, if albumin is low, that is again an anion ion which is low, so H plus ion will also be low. So if H plus ion is low, that is leading to metabolic alkalosis. So hypoalbuminemia results in metabolic alkalosis. If albumin is very high, then the A dot or the anions will be high. This will lead to metabolic acidosis. If phosphorus is very low, that happens in critically ill patient in DKA, the A dot is going to be reduced. And again, because anion is getting reduced, it leads to metabolic alkalosis. And if the anion is getting increased, that happens in CKD patients, the A dot is going to increase, and this increase phosphate or hyperphosphatemia leads to metabolic acidosis. Okay, and we know that in the CKD patient, metabolic acidosis, one of the major contributors is hyperphosphatemia. Okay, so if we compile all the things which we have read so far, if the patient is presenting to us in a situation of acidosis, so it can be either respiratory in nature or metabolic in nature. Respiratory, we know if the PCO2 is increased, then it is the respiratory. It is as similar to as in the traditional one, but the focus here is on the metabolic part. So if the acidosis is metabolic in nature, or it can have only two reasons. One, either the strong ion difference has reduced. That means either the sodium is reduced or chloride has increased, or the non-volatile weak acids, that is phosphorus or the protein, they have albumin, with it has increased. Okay, so these are the four major reasons for the metabolic acidosis. So if SID is reduced, then you have to further assess whether it is because of water excess, because water excess leads to hyponatremia. We know that the sodium disorders are related to water, so it is water excess, or there is imbalance of strong ions, either in the form of increased chloride, that is hyperchloremia, or increased unidentified anion, which has led to decrease in SID in the form of like lactic acidosis or ketosis that we see in DKA. Okay, so again I'm repeating, acidosis divided into metabolic and respiratory. Respiratory depending on PCO2. Metabolic, only two things can be there. One, it can have either strong ion difference which has reduced, or the A dot which has increased. If the SID is reduced, that means either the sodium is reduced or the water excess is there, or imbalance of strong anions is there in the form of increased chloride or increase in unidentified anion. And if the non-volatile weak acid has increased, either phosphorus or albumin would be increased. As we had discussed here about the unidentified anion, so far in the previous slide we have not discussed. So to identify this an unidentified anion, whether it is there or not in significant quantity, in traditional one we calculate the anion gap. Here we calculate the strong anion gap. Okay, so strong anion gap is the difference between the SID-A and SID-E. Okay, so SID-A is apparent SID, which is sodium, potassium, magnesium, calcium minus chloride and lactate. And SID-E is very complex. It is dependent on bicarbonate levels, albumin levels, and phosphorus levels, and it incorporates very complex equations, but we will simplify it in next few slides. And the difference between the two will give us the unidentified anion. Usually it will be very low or cannot measure it, and normal value is around 0. But in cases of DK and other things, we will see that this is going to increase. Now coming to the classification of alkalosis. So alkalosis, again, it can be metabolic in origin or respiratory in origin. If it is respiratory in origin, we will see that the CO2 levels will be reduced. But if it is metabolic in origin, it can have two reasons. One, the strong ion difference can be increased, or the non-volatile weak acid is reduced. Okay, if the strong ion difference is increased, that means sodium is high. That means the patient is having water deficit, or if the chloride is very low. Okay, and if the non-volatile weak acid is there, then the patient may be having either decreased albumin or decreased phosphorus. Right. So if we have these values, we can calculate all the things. What we need mainly is sodium, chloride, albumin, phosphorus, CO2. Okay, and if we have pH and bicarbonate, we can calculate other things as well. And that is what we are going to see in the Frankel modification of Stewart's approach. So coming to some clinical scenarios where Stewart's approach helps us in understanding the physiology behind some disorders. So what will happen if the patient presents to you with a water deficit? Okay, that can be because of DI, diuretics, evaporation, or patient is having severe vomitings. Okay, so in such a scenario, what will happen? Just for these are not actual values, these are just for understanding the principle. This has been taken from acidbase.org, which is the site which explains about the Stewart's principle in detail. Scenarios where the Stewart's principle applied and the principles are able to explain the reason behind the acid base changes. So first is water deficit. So what happens if you are excessively diuretic, if you receive excessive diuretics, or evaporation or DI has happened, or the patient has excessive vomitings. So this is the diagram is just for representation. So suppose this is normal plasma with a 1 liter fluid and sodium is 140, chloride is 102, and SID is here is 38. Assuming that these are the two major and strong cation and anion. So if there is evaporation and it is reduced to half liter, what will happen? The concentration will be doubled. Sodium will be doubled to 280, chloride will be doubled to 204. So the strong ion difference becomes 76. So SID here changes from 38 to 76. And we know that if the SID increases, it leads to alkalosis. And that is what we call as contraction alkalosis. So there is no change in the sodium content, no change in the chloride content, but just the change in the water leads to alkalosis, which we commonly call as contraction alkalosis. Second is water excess. So assuming that we have added the same plasma with 1 liter of water and we have now made it 2 liters. What will happen? The sodium will be half to 70, the chloride will be half to 51, and the difference will reduce to 19. So the SID, that is the strong ion difference, has been reduced to 19, and we know that if the SID decreases, it leads to acidosis. So excessive water leads to acidosis, reduced water leads to alkalosis. What will happen if there is change in the SID and weak acid? So this is normal situation where sodium is 140, calcium, magnesium, and potassium are there. The albumin phosphorus levels are phosphate levels are also there, and chloride is 102. SID here is 34 because we have included these things as well. So if there is hyperchloremic acidosis, what will happen? The chloride levels will be excessively increased. So if the chloride level is increased, then simply the strong ion difference reduces, and low strong ion is acidosis. So that is why hyperchloremia leads to acidosis as per the Stewart's principle. If there is hypochloremia, which happens in vomitings, it will lead to increase in SID, leading to alkalosis. If there is ketoacidosis or lactate acid acidosis, the sodium will remain same, chloride will remain same, but there will be an additional strong anion which in the form of lactate or keto, which will reduce the SID, again leading to acidosis. And if there is hypoalbuminemia or phosphatemia, this A tot will be reduced, and once this A tot is reduced, the SID increases, or the A tot reduction also leads to alkalosis. And if there is hyperphosphatemia, then the A tot will increase. Ultimately, it leads to acidosis. So this is the pictorial form of all the common complications which we see and are difficult to analyze by our traditional methods. Another very important explanation by the Stewart's approach is about the use of IV fluids. So, how does the saline causes acidosis? We are always hearing about that if we give large amount of dissociation of saline, it causes hyperchloremia. But how? And it leads to acidosis. But how? So here if we see that this is plasma where sodium is 140, chloride is 102, SID is 38. Now we have included 1 liter of NaCl to this plasma. Okay. So now what will happen? So this is 1 liter, this is 1 liter. The normal SID was 38 with a normal pH. So what will happen now? The plasma will become of 2 liters and the average of sodium will be 140 plus 154 which will be 147 and average of chloride will be 102 plus 154 divided by 2 which will be 128. Okay, so this is why the SID will become 147 minus 128 which will be 19. So the SID will be reduced from 38 to 19 and simply reduced SID increases acidosis and that is how hyperchloremia explains our acidosis, which is little difficult by the traditional approaches. What will happen if we give ringer lactates or the ringer lactate like other solutions? So what happens here is that this is a plasma sodium 140, chloride 102, SID is 38. We give 1 liter of ringer lactate. What happens is that here the cations are 137, chloride is 109, lactate is 28. So principle of electronegativity is maintained here. Okay, SID here is 0. So if we give this, what will happen? The SID should become half of that to 19? No. Why? Because once the ringer lactate goes into the body, it gets metabolized. The lactate gets metabolized and the lactate levels become 0. And that is why this 28 becomes 0 and that creates the change. So now what will be the level of sodium? 140 and 137 there. So it will be around 138.5 or 139. Chloride is 102 plus 109, it becomes 105. So the SID is reduced to 34. Just slight change here. And this lactate metabolism is the reason why these solutions, these are called as balance salt solutions because they do not change your strong ion difference by much and the patient's pH and the sodium chloride levels remains similar. Another very important explanation given by this principle is about the role of bicarbonate in increasing the pH. So traditional teaching is that since we give the patient sodium bicarbonate, bicarbonate levels are retained by the patient and since the bicarbonate levels are increased, that leads to metabolic alkalosis, right? So let's see what happens when we give bicarbonate in this patient. So suppose the patient is having hyperchloremic acidosis, sodium is 140, chloride is 130 and the strong ion difference here is 10, right? And in this 1 liter, we are giving 25 milliequivalent of sodium bicarbonate. So what will happen? The sodium will be increased by 25. So sodium will 140 plus 25 will be 165. Chloride is not there, so it will not change. So the SID will become 35. So here the SID, which was very low, has been increased from 10 to 35. These are just explanations. Okay, these are not actual things which are happening, but explaining the mechanism. Okay, so since the SID has increased from 10 to 35, increasing SID leads to alkalosis and pH becomes back to normal. So what we understand from this is that sodium bicarbonate increases the pH by increasing the SID. That is, the sodium is increased, but the other component chloride has not increased. And that is why it ultimately leads to alkalosis and not by the bicarbonate, which undergoes rapid metabolism and it is controlled by the CO2 and the respiration. Right? Now, how we come to if we have ABG in our hand, can we actually use it? Because we have already seen lot of equations are there. some mathematical complex equations were there, 6 equations, then polynomial and quadratic equation, very, very difficult for us, especially to do it rapidly and at bedside. But there are some scientists which have tried to simplify these things, and Frankel is one of them. And now many of the people use Frankel Stewart's approach. And what is this approach? So this is the simplified Steward of the Frankel's approach. So we know that the PCO2 is, as in other approach, we have to analyze in that way only. But as per the Frankel's approach, first we have to see what is the sodium levels, whether there is any deviation is there from normal. Normal they consider around 140 plus minus 2. And we know that the sodium disorders are actually water disorders. So if there is hyponatremia, that means there is water excess. And if there is hypernatremia, that means it is water deficit is there. The step 2 is to check for the chloride excess or deficit, and it needs to be corrected for changes in the water excess or deficit or according to the sodium levels. If the sodium is out of range, then the chloride is expected to change according to the sodium, and that is why chloride correction is done, which is equal to observed chloride into normal sodium levels divided by the observed sodium levels. And the normal value of this corrected chloride is 102. Then the third thing which we have to calculate is the calculation of the apparent strong ion difference. This apparent strong ion difference is the calculation of bicarbonate, albumin, and the phosphorus. Okay, why this apparent chloride? So if we remember that the strong ion difference is equal to the difference between the strong cations and strong anions, and it becomes weak anions. And weak anions largely have three components: bicarbonate and A-tot, and A-tot has albumin and phosphorus. That is why SID can be calculated in other way as well, in the form of HCO3, albumin, and phosphorus. HCO3 we can get from ABG. Albumin we usually get from our labs in the form of gram per liter, and it can be converted into the milliequivalent per liter by multiplying it by 0.25. If you have per deciliter, then you have to multiply by 2.5. And phosphorus we have in milligram per dl, so you have to convert it into milliequivalent per liter in the form of 0.6 multiplied by the phosphate levels. So you calculate albumin level, you calculate phosphate level. We know that these things can have direct impact on acidosis and alkalosis, and then we also calculate the SID. So three calculations are there here. And lastly, we have to calculate the unmeasured strong ion, which is the strong ion gap, or in traditional one we call as anion gap. So this is equal to sodium chloride, sodium, potassium, calcium, magnesium, and minus the chloride level. This is the strong anion, and the strong ion difference, or the SIDA. So this becomes SIG. Okay. The normal level is around 8. Right. So these are all the calculations. Again, summarize. So step 1 is to see PCO2. PCO2 will give us idea about the respiratory disorder. The normal level is 40 plus minus 2. Step 2 is to see the sodium. Sodium will denote the water problem. The normal level is 140 plus minus 2. Then step 3 will be the calculate the corrected chloride. Corrected chloride is equal to observed chloride into normal sodium divided by the observed sodium. The normal value is 102. Albumin in milliequivalent is equal to 0.25 into albumin, and in gram per deciliter, its normal value is around 38, or in this is gram per liter. In deciliter, it is 3.8. Phosphorus is in PI is equal to 0.6 into phosphate in milligram per dl. The normal is around 3 milligram per dl. SID will be the equation where HCO3, albumin, and phosphorus, all these three things will be combined, and if the normal is around 39 plus minus 1. And SIG is difference between sodium, potassium, calcium, magnesium minus the chloride and the SID, and it is 8 plus minus 2. Okay. PCO2 will give respiration, and SID will give you about the strong ion difference. Albumin, phosphorus will give you A-tot, and the difference between the all these things will give you the SIG, which is the unmeasured anions. And if the sodium level is reducing or the SID is reducing, that will cause acidifying effect. And if the chloride, albumin, phosphorus, they are increasing, they will also cause the acidifying. Minus things are increasing, that is acidifying. Plus things are decreasing, that is acidifying. And reverse is true. If the sodium is increasing, that is the cations are increasing, that is alkalizer. If the anions are decreasing, that is alkalizer. Okay. So coming to one case here, we have a 72-year-old man who is a known case of type 2 diabetes, CHF, renal failure, is admitted with nausea, vomiting, and shortness of breath. He is on diuretics and insulin. His blood pressures are okay, pulse is 98, and respiratory rate is 18. We do an ABG. Okay. Let's see what happens if when we see an ABG. Will Steward's approach help us or not? So we get in this ABG. ABG shows pH 7.4, PCO2 40, PO2 92, bicarbonate 24, and these are the electrolytes which we get. Traditionally, we always look at the pH, PCO2, and bicarbonate, and we see here that the pH is normal, absolutely well. PCO2 is absolutely normal, and bicarbonate is absolutely normal. So traditional approach, everything is normal, and we don't have the base excess, so we don't know. Probably this is also normal. So either it is absolutely normal, that means that there is no primary disorder, or if we see the Stewart's approach, can we get something else, or that is also showing us the normality? Let's see. Step 1 was to calculate the CO2, to see the CO2. Okay, CO2 is 40, it is normal, no disorder, respiratory disorder is there, absolutely clear. Step 2 is to see the sodium level. Sodium level is 140. This is also normal, so no water excess deficit is majorly here. Step 2, again, next is corrected chloride. Corrected chloride is 95. Chloride is 95, 142, and 140. Okay, I think it should be 140. So it will be 95. 95 here is on a lower side. Low chloride means there is some alkalization effect of the low chloride is there. That means some alkalosis in the form of hypochloremic alkalosis is definitely there. Okay. Now, if some alkalosis is there and we see that the patient's pH is normal, that means some other thing is also going on which is causing acidosis. Okay. Let's see whether this Stewart's approach is able to find it out. We see the next step, which is the albumin level. Albumin level is 35. It is only slightly low. So normal is around 38. Mild alkalizing effect of hypoalbuminemia is there. Phosphorus level is 2. Again, it is just slightly low. Again, that means that mild effect of alkalization is there from the phosphorus. Let's see the next step. Next step is to calculate the SID. SID is equal to bicarbonate plus albumin converted into milliequivalent per liter and phosphorus converted into milliequivalent per liter. And I've already done the calculation and it comes out to be 34. It is also slightly low, which is kind of expected because we see that two components are slightly low. So this is also causing little of alkalization effect. And last step is to check for the strong ion gap. Strong ion gap is equal to sodium, potassium, calcium, magnesium minus chloride and the SID. It comes out to be 20, and 20 means the normal value is around 8, and here it is coming out to be 20. That means it is very, very increased. Okay, so this is very high, and that means there is some anion gap is there which is acidifying the whole situation. Right? So the Stewart's approach has been able to identify, and the first and the easiest thing which give us the hint that not everything is normal is the presence of hypochloremia. Once we see that there is disturbance in the sodium or in the chloride, that means some definitely metabolic problem is there. If chloride is low, that means metabolic alkalosis is there. And when we see that the ABG is showing a normal pH and the PCO2 and bicarbonates are normal, that means there is something else which is able to compensate for this hypochloremia related metabolic alkalosis, and some acidifying disease is there. And when we see all the steps, we are able to find out that there is some high strong ion gap which is leading to acidifying. So what is the ultimate So there is alkalinization by hyperchloremia and partially by the hypoalbuminemia and phosphatemia in response to unmeasured high anion gap metabolic acidosis, right? So this is the diagnosis of this patient. So by traditional approach, we were not able to get any information. By using Stewart's approach, we have been able to solve this complex ABG, which seemed to be very. We see another case. The following data from the arterial blood gas analysis of a 71-year-old male admitted with septic shock and has been resuscitated with normal saline. Okay, we see the ABG 7.22, PCO2 32, PO2 82, bicarbonate 14, electrolytes are there. We see here that there is acidosis is there, and majorly it is metabolic acidosis. And so this is metabolic acidosis, and patient is trying to compensate by having little bit of respiratory alkalosis, but this is not fully compensated. Okay, so this is our traditional answer. Okay. What is the Stewart's answer? CO2 is on the lower side. So there is respiratory alkalization is there, of course. Sodium we see 147. 147 is higher than 140. So high sodium is alkalinization. So again, this is also causing alkalinization. So some parameter will be acidifying, especially since the pH is also on the lower side. Correct. Next step is chloride. Chloride 126 is the chloride in this patient, very high. And the corrected chloride, because sodium was also on the higher side, so correction is a little bit reduced it to 119. Corrected chloride becomes 119. 119 is also very high. It has increased from 100 to 119. So the change is very, very significant. So this is strong acidifying. We see albumin on a lower side. When it is low, then it is alkalinization. Little bit of alkalinization is there from albumin. Phosphorus we see normal. Then we calculate the strong ion difference. It is bicarbonate plus corrected albumin and phosphorus corrected. And the calculation is 23. 23 is little bit of low. So SID is little low. So it is acidifying again. And we calculate the SIG. SIG is all the cations minus chloride minus the SID, which is comes out to be 6. 6 means that this is normal. That means here there are two things which are causing acidification. One is hyperchloremia, and that is leading to low SID, leading to acidifying. So this is a low SID because of excess chloride, and that has been partially offsetted by the alkalinization effect of hypoalbuminemia and the respiratory alkalosis. And this is what is expected, because in the history we know that this patient received sodium chloride resuscitation. Okay, and normal saline resuscitation has led to this excessive hyperchloremic acidosis. Right. So this is how you can use your step-by-step approach in analyzing your bedside ABGs. So now we summarize. So the Stewart's approach to acid-base balance is a fascinating method that is increasingly being used, especially because we have now the apps very readily available. This implies that both approaches are mathematically compatible, and the Stewart's approach may provide the overall and the bigger picture. They are independent variables there, with 3 in counting. These 3 independent variables are SID, ATOT, and PaCO2. From this, we classify our acid-base balance in the form of alkalosis and acidosis. Respiratory is similar to what we see in the traditional one. Hypocarbia leads to respiratory alkalosis, hypercarbia leads to respiratory acidosis. But the metabolic classification is little different. It can be either because of strong ion difference or abnormal ATOT. Okay, and strong ion difference, it can be because of sodium disorder, which is actually water disorder. So if water deficit is there, that leads to hypernatremia. It leads to contraction alkalosis, metabolic alkalosis. If there is a water excess, this leads to dilutional acidosis or hyponatremia. And if abnormal strong anion is there, the chloride If it is low, then it causes alkalosis. If it is high, it causes acidosis. Unmeasured iron, if increases, then it also causes acidosis. And in the weak acid, if albumin and phosphorus are low, then it causes alkalosis. And if they are high, then it causes acidosis. So minus things, if they are low, and the plus thing which is high, that it causes alkalosis. Anions which are high or cations which are low causes acidosis. The advantage of this approach is that it gives you mathematical explanation of acid-base disorders. It is more scientific and accessible and logical framework for design of resuscitation fluid is based on this principle, and it attributes an appropriately low importance to the bicarbonate, as we have seen in the transfusion of the sodium bicarbonate, which was actually leading to increasing in the SID. The disadvantage is that it is complex, it needs many variables. Though now we have the simplified approach, there is substantial difference to the well-validated classical approach. Classical approach we have been using for decades, and it has served and it has been able to explain us many things. So if we know both the things, that can produce confusion. It requires a lot of variables, and each measured with a small error can lead to amplifying of the measurement area. Error fails to incorporate the buffering contribution of the hemoglobin, because in this whole hemoglobin is not there, and there is no evidence. This is very important, and lot of papers are there. And it says that no evidence has been able to show influence on mortality with the help of this approach, and that is why it is still not used at bedside as much as possible. But can we compare the two and try to mix it up? I think we can do it. Just we see that the classical acid-base disorder and corresponding physicochemical disorder, we can understand and improve our knowledge, and we can try to incorporate both the worlds and combine it into a single thing which will be helpful for our patients. So we know that we have respiratory acidosis and alkalosis depending on the CO2 levels. Both the disorders agree on that. If in high anion gap metabolic acidosis, which is formed from anion gap calculation in classical one and SIG in the physicochemical one, we have the reasons ketones, lactates, toxic anions, and non-volatile acids, including the phosphate. Here, the metabolic acidosis can be converted into high TOT acidosis. High ATOT acidosis includes ketones, lactates, formates, non-volatile like phosphates, and high albumin. Although clinically we rarely see high albumin, but giving albumin can cause acidosis. This can be explained from this particular slide. The other can be normal anion gap metabolic acidosis, which is bicarbonate loss. This bicarbonate loss actually happens because of the low SID acidosis. Okay, so when acidosis is because of two things, high ATOT or low SID. So low SID is either chloride has increased or sodium loss is there. And in the metabolic alkalosis, traditional teaching says either it is bicarbonate gain or acid loss, or maintenance factors which prevent renal bicarbonate handling, which is a chloride depression, potassium depletion, poor renal function, and volume depletion. As per the Steward's approach, it can be explained in the form of high SID alkalosis, which is chloride loss or sodium gain, or low ATOT alkalosis, which is low albumin and phosphate. So all the metabolic things can be explained by chloride increase, decrease, sodium increase, decrease, and mainly albumin increase and decrease. So if we have these three things, and which we have for most of us, we can find some middle ground. And if we cannot calculate all the equations, and we cannot remove or remember all the equations, especially in complex metabolic disorders, if we see that there is some sodium chloride or albumin levels which are varying, definitely Steward's approach will be able to guide us better, and it is going to help us in finding what is the basic mechanism which is causing the problem. And if we are still very much convinced with the traditional approach, I recommend that from the Steward's approach, use sodium chloride and albumin and add anion gap analysis to all of your patients. And albumin correction is also must be added in all your analysis, because as we have seen in initial slides, the traditional approaches only takes the bicarbonate buffer as the main buffering thing, but we know that the albumin and the phosphorus buffer is also happening side by side. Although the phosphate levels are very low, so that can be excluded, but albumin correction should not be excluded, especially if there is severe hypoalbuminemia, which we see very often in our septic patients, right? So probably this is how we can further improve our ABG analysis. Thank you.